Welcome to the lecture OX15, Programming Languages, where we're going to talk about some aspects of programming languages, how programming languages can foster security, but also how they can hinder security. And there's an interesting trade-off between performance and security that we're also going to discuss, which has hindered the deployment of safer programming languages for quite a while. Some of you have wondered, also just a little note on the side on a low-level aspect. Some of you have wondered what the numbering scheme comes from and asked questions. So these are hex numbers, right, starting with OX. And then I'm using two nibbles. One nibble to just increment the class number, going from 0 to, what is it, I think like 15 total. And the other nibble I'm using to encode a second set of information, which is which major block that we are in. We're now in a second major block that covers a bunch like programming languages, data security from last week, and so on. So you can figure out for which quiz it is by looking at this nibble, and you can look at which class it is by looking at this nibble. And two nibbles together give you a byte. And everything is nicely encoded in a byte. This is a little head nod towards systems programming in C, where you're often using any space available, right? So we are encoding in 1 byte of information, 2 layers of information, a class number, and then we're using a couple of bits to encode which major block it is. I thought this was a fun head nod and a pun towards systems programming. And yeah, if you were wondering, this is it. Programming languages. Learning goals for today. We're going to cover different sets of programming languages, as I mentioned. You don't need to be expert in all of these programming languages. We don't expect you to become experts in any of these programming languages. But what you should get is a feeling or an understanding of the safety guards that different languages provide and the trade-offs they offer. You can have bugs in any programming language, but some programming languages make it easier for you to have bugs, and certain bug classes that are possible or not possible in different targets. So we're going to look at some modern programming languages and also figure out how they achieve certain safety properties such as memory safety, type safety, concurrency safety, or whatnot. And then differentiate, as I said, between type safety, memory safety, and thread safety as different policies that can be supported by the runtime system or by the language itself. And then finally, we'll also mention defense in depth to some extent, and sandboxing and compartmentalization, how this can tie different things together. Starting with a motivation on why we need this. Who knows this book? 1, 2, 4. Okay. Who has read it? Who has taken a course that used this book? Okay, a bunch. The people that know the book or have taken a course on the book is strictly larger than the people that have read the book, which is also an interesting take on the current generation reading books. It's still highly recommended. It's what is known as the Dragon Book. If somebody talks to you about the Dragon Book, you now know why it's called the Dragon Book. Because there's a dragon on the cover, right? If you just Google for the name, this additional semantic information is not covered. Now, why is there a dragon? Because the programmer needs to slay the dragon to write the compiler for different systems. So this is a classic compiler book which covers interesting topics that you read before going to sleep, such as parsing, different kind of programming languages, efficient parsing, data formats, syntax trees, and whatnot for these different systems. It's like the default book on compilers with a heavy focus on parsing and data formats. which is an interesting target. This was like the foundation for compilers. And compilers are like already even the first programming languages, the most low level. Sorry. The most low-level programming languages were. Give me a second. This is so exciting. So the first programming languages like C, which are now considered extremely low-level, extremely close to the hardware, and also the most efficient ones. They were initially considered extremely bloated, resulting in a fairly high overhead when running them. So people initially considered that compilers were somewhat a waste of time, or not a waste of time, but a waste of performance, because even a C compiler was much less efficient than assembly code that could be written by a skilled developer. Now, what are the key benefits of using a compiler compared to writing assembly code? Yeah?
You can compile for different hardware platforms.
You can write once, you can compile multiple times. Yeah, that's one big advantage, right? You can you can take the same code and then compile it towards multiple architectures with like some minor modifications. Yeah, what else?
Development cycle because you're writing on a higher thing.
Yeah, that's a good reason. For example,
instead of writing assembly, you write C or even higher.
yeah, what's an example of a benefit of writing in a higher level language? What's an instance of one of these abstractions that you're using?
Built-in functions?
Say again?
Built-in functions.
Built-in functions? Yeah, you can have built-in functions in assembly, right? You can use libraries and call functions in assembly too. But I've given it away, right? Like we're at the
Easier to read.
easier to read, sure. So maintenance is cheaper. What else? It gives you abstractions, such as functions, right? Functions are an amazing abstraction that make your life as a programmer much easier. In assembly, you can, you control flow, you control register assignments, everything else. You're as close to the hardware as it gets, but then you're also responsible for clearing registers, passing the parameters when you're calling a function and whatnot. And all these interfaces across functions, across methods, across systems, data formats and whatnot. You don't need to worry about bits and bytes usually, but you just use whatever the language provides. And this makes this much nicer and much lower. You don't need to think about it, right? So the compiler takes away simplifies the coding of the program, and you can focus on the algorithm, you can focus on the structure, you can focus on the functionality without having to focus on, oh, for this function that I'm calling here, how did I pass the parameter? Did I pass the first argument in R15 or did I pass the first argument in R2? What about the other sequence? How do I return arguments? Like where's the return value of the function? What's the type, right? The compiler takes away all of this, even for the simplest language like C. So what we are seeing right now is that there's quite a bit of bad press on systems languages like C and C++. They're still considered the most efficient programming languages, but coming at a price, right? Nowadays, people rarely write assembly code. If something needs to be efficient, it's usually written in C and C++, but we're trying to lift these languages also up to a somewhat higher level of abstraction, making it safer overall. For C, this is not easily possible. That's why we're shifting to somewhat alternate languages. But for C++, we're seeing a lot of development towards safer standards of it. One of the motivations for like moving or pushing towards these safer languages is that we can get rid of whole classes of bugs. Instead of having good practices of finding bugs or reviewing code or whatnot, or developing automated techniques, by moving to safer languages or safer dialects of languages, we can just get rid of whole classes of bugs and vulnerabilities. There's a couple of interesting articles that I'm referencing. The Google security blog pointing at using Rust in the Android platform, where they are now writing more code in Rust than in C and C++, and any new code, with the goal of any new code being developed that should be in Rust, any new systems code. And they're pushing more and more Rust components into Android as a system, because Rust is getting rid of the underlying memory safety issues that plague C and C++. So it's an interesting development that we are somewhat phasing out C and C++, but also it poses an interesting question: what do we do with all of the legacy code that's still out there? Now, when we're looking at security, there's usually a take 2 out of 3, right? So at Google, when you're writing code, you can pick 2 out of these 3 corners, like 2 out of these three options. So your code, there's code that processes untrustworthy input. That's a fact, right? It's if your code needs to handle the data that is being passed in from a potentially malicious user. There's code without a strong sandbox, or code written in an unsafe language. And in their internal guidelines, you can pick 2 out of 3. Don't write code that processes potentially malicious inputs without a strong sandbox in an unsafe language. Essentially, you can write code that processes untrustworthy input in C or C++ if it's strongly sandboxed. What would be a good example of such a piece of code? Yeah? Say again?
Pseudofont in Linux.
It processes untrustworthy input, right? Yeah. So this would be all 3. This is Doom. In the what's the application you use most? The browser. And in the browser, there's the renderer component, which is written in C and C++, but it's strongly sandboxed. Right? So it's a good example of such a component. There's in Android, there's a couple of new libraries that are written in Rust and therefore no longer need to be sandboxed, moving or reducing the overhead that the sandbox actually introduces. Question?
What's the sandbox?
A sandbox is you're not letting the code run on your system without checks. If you're running a process on your system, by default, it has all the privileges of your user. Right? It doesn't matter if you're running copy or if you're running rm to delete all the files, or if you're running OpenOffice, or if you're running a browser. Like all of these programs, if you are running them as your user, they have access to all the files in your user directory, to all the privileges that you as a user have, and all the system calls that you as a user can execute. Ideally, you would differentiate a bit. We've talked about this just a little bit with, in access control, that you could have policies on a per application basis. Right? Not every application needs to have unmediated full access to all your data in your home directory. Right? So you could restrict this further. Cool. Other questions? So 2 out of 3. And if your code processes does not process potentially attacker controlled input, you can write it in any language you want. But again, the question becomes, if you're selecting a programming language, like what ecosystem you want to run it, you want to develop it in. And most people today would choose a more high-level language just because of the, I think as you mentioned, the availability of tooling and libraries. The more nicer libraries are available, the easier it gets to write your programs. So consequences of memory safety vulnerabilities, we see that that memory safety vulnerabilities are quite severe. These are just like a statistics of different kind of vulnerabilities that are being used. Blue is are memory safety vulnerabilities, red are others. So 11 out of 12 observed vulnerabilities with critical severity or memory safety, remotely reachable, like 33 out of 36, confirmed in a wild exploits that were actually observed as being exploited were also mostly memory safety vulnerabilities. So the current exploit ecosystem leverages vulnerabilities in programs that are written in low-level languages like C and C++ that are prone to memory safety vulnerabilities. Memory safety vulnerabilities, like just 2 years ago, were 36% of all vulnerabilities in the CVE database. That's a common list of vulnerabilities that tracks or gives unique identifiers to individual vulnerabilities. 86% of critical severity security vulnerabilities, which is the highest rating that it gets, and 89% of remotely exploitable vulnerabilities. Now, this means that this is a big deal, right? Most of the exploits that happen, or most of the bugs that are actually being exploited, are due to memory safety vulnerabilities. Now, interestingly, right, this is the baseline system. So when you're writing C and C++ code, you have to be aware of these kind of potential issues that can happen. And as we see, they are very, very common. There's just a screenshot from like 2 weeks ago on Sysbot. Who knows what Sysbot is? Just a quick show of hand. 0. 1. So Sysbot is an online platform that does continuous fuzzing of the Linux kernel. Fuzzing is an automated testing technique that we'll cover in a bit more depth later in the course. It's been the most efficient or most successful technique at finding bugs and vulnerabilities in different systems. Now, this is an automated process. It fuzzes the Linux kernel and tries to find new issues whenever they crop up. At any point in time, there's around 1,000 plus unassigned and unfixed bugs available on this platform. It's a public website that just prints the result of all of those issues. And when we scanned 150 of these bugs were different kind of memory corruption errors that are currently unfixed in the Linux kernel. And these are just open bugs and vulnerabilities that will need to be fixed at one point in time. Right? So they are very, very common and out there. So you can check for yourself the Sysbot list and then see if you can find any fun vulnerabilities that you want to look at. 70% of Android's high severity vulnerabilities in 2021 were on low-level code due to memory safety issues. And since Android 13, Google pushed quite a bit the use of safer languages such as Rust and potentially Go on the server end. And we also see that the number of memory safety vulnerabilities reported in the Android-based system, at least, has declined since then. Which also means that we are making somewhat progress, but there's still quite a bit of vulnerabilities remaining. The first memory safety vulnerability, or the first like large malware that took down the internet was the Morris worm that I want to mention. And I'm a huge fan of the cleverness of the worm. Who's aware of the Morris worm? 1, 2. Okay, what did it do? You already gave an answer. There were 2 or 3 more people that were aware of it. Does anybody want to speak up? Yeah.
It reproduced itself.
It reproduced itself, yes, and thereby took down the whole of the internet. Does anybody know what kind of functionality it used to reproduce itself? The reason I'm bringing this up, that it used a combination of 3 techniques that are in like the mid-late 80s, that are still the most dominant techniques on how malware reproduces itself. So it used a combination of a memory safety vulnerability, a command injection vulnerability, and weak passwords. So the worm had 3 exploitation vectors. When it infected a host, it scanned for other nearby hosts and tried to infect those. The first thing it did, it tried to exploit a stack-based buffer overflow in the remote listing of logged in people, right? So which was a service that Unix systems had at the time. You could supply a username and pretty much ask over a shell, is this user logged in on the remote machine at the moment? People thought this was a useful service at the time, right? And by copying the username, there was a stack-based overflow because the length of the username was not checked. And if the attackers applied a very long username, it overrode parts on the other parts on the stack, including the return instruction pointer, which allowed the worm to inject shellcode that then jumped back to this buffer and executed arbitrary code, which was a short program to download the worm and execute it as root. Right? So it was the first attack vector. A stack-based buffer overflow that allowed arbitrary code injection, arbitrary code execution. The second one was an arbitrary command injection. So what's the difference, right? Arbitrary command injection was in SendMail. So SendMail was the most common email program at the time, server program for sending and receiving emails. And in the default configuration, it allowed the setting of a feature that said, I now want to execute an arbitrary command. This was supposed to be a debug feature that when you're testing the email server, that you could run an additional command to, for example, drop a file or print a string or whatnot. Right? This was meant for debugging purposes, but it was left in the build. So the worm connected to the mail server said, hello, I would like to send an email. And by the way, please execute this command, which was copy the worm to the local machine and execute it. And SendMail happily did that. This is called a command injection vulnerability, which allows the SendMail, the attacker, to execute a command as the user running the SendMail daemon, which was root. Right? So that was the second one. The third one was the weak passwords. So the worm had a list of 100 or so well-known usernames and passwords and just tried logging in with each of these individual passwords. If you think about this, these 3 attack vectors that were premiered in this worm in the late 80s are still the dominant attack vectors against software. Abusing some form of memory corruption to take control over the control flow of a program and then inject new code and execute it. That's a dominant attack vector. Finding some kind of command injection vulnerabilities is another dominant attack vector, or just probing usernames and weak passwords, which is another key attack vector. So the question you could ask yourself, what has changed over the last almost 40 years since we had this initial first worm that took down all of the internet. Now, we've made quite a bit of progress, right? So this worm was written by like a student that just did this for fun and giggles. He was an expert in security, an expert in programming, but still, it was done by one student. Now, exploits are written by usually multiple people, and if you look at nation-state malware, this is done by teams of 100+ people, right? So the cost of developing an exploit grew quite a bit, and it became much more professional. So the cost of exploitation has risen, which is good, right? So we're making some form of progress. But similar bugs as almost 40 years ago still exist. Now, interestingly, back in the days, we had about 1 million lines of code that was out there, all written in low-level systems languages. And in the discussion around this worm, it was that it's too hard to fix 1 million lines of code and to rewrite it in a safe language. So the argument was that it's going to be too expensive if we rewrite 1 million lines of code. Now, Google Chrome has 100 million lines of code. Right? It's 100 times bigger, so 2 orders of magnitude more. If you're looking at the server code that Google is running, we're looking at billions of lines of code. Right? So we're like 3, 4, 5, 6 orders of magnitude over the amount of code that we had to protect in the 80s. So looking back, we likely should have rewritten the code in the 80s and be done with it. Now we have a problem that's 4 or 5 orders of magnitude bigger, which is an interesting problem to have, and also an interesting study in economics. Right? It was considered too expensive back then. It's still too expensive, which is likely resulting in that we are going to rely on low-level code or systems code written in unsafe languages over the next decades or even multiple generations of programmer lives. Now, another question we can ask ourselves is if is a safe language actually better for security? And there's an interesting push that the NSA recommends using a memory-safe language when possible, while the use of added protections to non-memory-safe languages and the use of memory-safe languages do not provide absolute protection against exploitable memory issues. They do provide considerable protection. Now, what's the cost of switching to a safe programming language? What's the trade-off? What do you folks think? Yeah?
Is to rewrite 100 billion line of code from unsafe language to safe language. It takes a lot of time and resources.
Yeah, so it's going to be costly.
Yes.
We're just going to use an LLM to rewrite it. It's going to be fine. And then just run it. But yeah, severe, massive cost. Yes?
Performance.
Performance? What regarding performance?
Well, I guess a low language it perform more than a high language.
Yeah, so performance could be an issue. Yeah?
You have less power for manipulation of the memory.
Say again?
That's less power of manipulation of the memory.
So you have less control over placement, structures, and whatnot. Yes, and especially when you're thinking about writing a driver, or when you're interfacing with something outside of your control. Let's say you're writing a driver for a network card. The network card expects memory precisely in this layout, right? Because you cannot recompile a network card. That's a piece of hardware, right? So you have to follow the specification of the hardware. So you need to define this and need to define this interface somehow. Yeah? What else?
Maybe here is trying to fix issues with the permissions language. You might expose yourself to new bugs or issues.
Yeah. Interestingly, rewriting is not always better. Because the old code, as you mentioned, has gone through many iterations, right? And most of the bugs will be fixed. Now, if you rewrite, most of the bugs are in new code. So if you rewrite in a safe language, you're not going to have memory safety bugs, but you're going to have a lot of other bugs, right? That were fixed in this old piece of code. Anything else? So yeah, there's an interesting trade-off. Rewriting certainly comes at a cost. It may come like at a personal cost. It may come at a performance cost. Sometimes we are limited with the underlying hardware that we are looking at, but also there's a trade-off of how much we want to rewrite or at what pace we want to rewrite. So common best standards are to write new code in safe languages, and as we are moving forward, code will be rewritten at a time, and then we can just get rid of the old code. Today we're going to look at 3 types of safety: type safety, memory safety, and threat safety, all in with an individual discussion. Let's look at type safety. And type safety tries to give data a type. Underlying computing system, or at least the computers we use today, are not aware of types. To a computer, it's just memory. Everything are bits and bytes in memory somewhere, and you're just bit banging around and moving bits from one place to another, right? The CPU does not care if this is your fancy whatever box type or not. The only thing we have is individual instructions that are executed by the CPU. The CPU simply executes the instruction you point at. You've got a flat address space somewhere in memory. You have one pointer that says this is where my code is, and the bytes that are at these locations are being interpreted by the CPU as instructions. And you've got a couple of other pointers that point into somewhere into memory where your data is. And there's no inherent difference between the data and the instructions. All of it is just bytes somewhere in memory. Now, conceptually, what we are trying to introduce here in programming languages is a type system, which is a logical abstract system that assigns a type to every term, like a variable, an expression, a function, or whatnot. The type of a value specifies which operations can be applied to it and how you can apply different kind of operations. Also, the type of the variable limits values it can be assigned. So, for example, an integer can only take integer values like 1, 2, 3, 4, 5, and not a fraction of it, right? Same for a DOM object cannot store JavaScript, or an image is an image type, depending on the type that you define in your system. The type of an expression or function delimits values it accepts and can produce. So it defines what kind of data are being taken in and what data is being returned. And there's many different type systems that exist today. There's static typing, dynamic typing, declared typing, inferred, or strict and relaxed. These are 3 different dimensions of type systems. So a type system can be like it's always pick one of each dimension. It can be static, declared, relaxed, or it can be dynamic, inferred, relaxed. This would be Python. Static, declared, relaxed. This would be C, right? So you can pick and choose from all of these dimensions. And let's now quickly discuss what these 3 different dimensions are. After we come up with a bunch of terms. First, type safety. Type safety means that the program is following your declared types to some extent. And it kind of goes back to Robin Milner, who said that well-typed programs cannot go wrong. As in, if your type system is sound, then expressions accepted by the type system must evaluate to a value of the appropriate type. A language is type safe if the only operations that can be performed on data in the language are those sanctioned by the type of data. So type safety depends on the language. This is a language feature and kind of influenced by the static dynamic semantics, both of which can be type safe. So type safety defines that your program must follow the given type systems, or only operations in this type system are allowed. This is rather abstract so far, so we'll go through a couple of steps to concretize this information. Static or dynamic typing. So a static type system allows checking by a compiler, which means that we can check ahead of time if the program follows the type definitions. So the type checker uses different kind of typing rules to determine the type of all the terms, compare infer types against declare types, and operations performed on the values. And any mismatch is a typing error. Whereas a dynamic system tracks type of objects at runtime, and then just infers, prevents improper operation whenever the operation happens. You may have seen in Python, right? You wrote your beautiful script, it computes for 4 days, and then you have a type error when you're printing the object and it just fails. This is a runtime check. Or if you're writing a program in Rust and you try to compile and the compiler says no, you know that the issue, you know about the issue ahead of time. So in this example here, we've got this simple function. We're calling this function which returns n times 2, the parameter n times 2. We call it once as an integer, once as a float. In most static systems without type conversions, this is an error, since the system will infer, oh, this is an integer, so we'll happily accept this as integer only. And then when it sees a float later on, after it has defined function f of being taking an argument of integer type, it will throw an error because the typing information that the compiler inferred is tied to the function. It says this is an integer argument. I've learned this through this abstraction here. Now I see a float and I will throw an error because it's not an integer argument. In dynamic languages, this is becoming a boxed integer value, this is becoming a boxed float value, and then the multiplication operation is defined on both types. So the interpreter or runtime system would simply run the two function calls. First, n is an int, then it takes the multiplication operations for int, multiplies it, or the value is a float, and it takes the multiplication operation for floats. Some pros, cons for static typing. They're checked at runtime, at compile time, and there's no runtime overhead, so which means it is usually more performant. You find errors before the program runs, you find all the errors, and it's great to build reliable systems that you can actually reason about. Dynamic is much more flexible, so you don't need to worry about satisfying the compiler, right? You can just go ahead and hack it out. There's much fewer type declarations that you need to do. And it's great for quick and dirty programming, such as scripting. This is why you usually see, if you look at scripting languages like Python, they usually go for dynamic typing because it's much lower effort, and you can quickly churn out a lot of code for prototyping. Whereas if you look for larger scale systems, it would be a pain to build to develop Google Chrome in Python, right? Just from the type system, because you want to support the support of the compiler to tell you, hey, this one is not working out, you need to adjust it. Declared inferred types, usually, or until some couple of years ago, most programming languages required full type declarations. So for each function that you define, for each variable you define, you need to tell the compiler or the runtime system what type it is. So this is an integer, this is a float, this is a string, this is an array, this is whatnot. Compilers only infer the expression types, and then they use the variable types as a baseline to then translate to the expression types. Now, Haskell introduced a concept of type inference, where the types are automatically inferred by the compiler as it passes through the system. And this later spreads to other languages that are more commonly used. So declare function argument and result type, and the compiler just infers everything in the function body. There's extensions in Scala, C#, Java, TypeScript, and whatnot, where it does all of that. So for example, it may infer this is a float for n, this must be an int, and then it can go through the individual details. And only when there's a violation, it will throw out an error. So it used to be declared only. Now we're moving to more and more inferred. How do you tell the compiler that you want to infer a type in C++? There's a new keyword that was introduced a couple of years ago. No constraint. Auto, right? Auto variable equals blah, which tells the compiler, please infer the type of this variable. Or it tells you, I'm too lazy to type the variable type, please infer it for me as you go along. So auto is a keyword that was added to C++ to bring inferred typing to this programming language. Strict, relaxed, trade-off. C is not strict, C is very relaxed. It trusts the programmer with the type conversion, which means in C, you can always cast any kind of object into a char array and thereby violate the underlying type system, or not violate, but it's pretty much, it trusts the programmer. In C, as the programmer, you have ultimate power, right? You can say, yeah, this looks like an integer value, but I'm going to treat this as a pointer from now on. And you can just force the type conversion from an integer value to a pointer. Or you can add 2 pointers, which is also undefined. Or you can subtract 2 pointers. Again, in most other type systems, this would not be possible. Why would you want to subtract 2 pointers? For example. For the length, to figure out the length of an array, right? You've got a pointer to the beginning of an array and a pointer towards the end of the array. You want to figure out how many elements are in there, you subtract the 2, right? Which usually works out if everything is laid out flat in memory as an array, right? So in C, this is usually the case. But the operation of just subtracting 2 pointers is not defined. Pointers don't have a subtract operations. And in C, this is very relaxed, right? Because it doesn't enforce any kind of limit. So yeah, this is another example, right? Here we are defining an object where we're saying this is a integer length, the length of the string, and char, this is the first character, right? The first character of the string, right? So a memory object, this is a length, which is a 4-byte value, and then we've got 1 byte for the first character of the string. Now, interestingly, when we do something with this string, struct string string, we allocate the size of this str, like of this structure, and the length of the string. We store the length of the string in this variable, all good, and then we copy the string that is passed as a parameter into in here. How can this work? Right, so if you look at this, what we have allocated is pretty much this object here, right? That's the, and how do we call it first? And this is of type char, this is of type integer. Now what we've done is, let's say we write the string that we pass as a parameter is hello world. We write here hello world. New line, or just a 0 byte, that's okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's say 11, right? We don't want to store a 0 byte. Good. So there's 11 characters, so we're going to write 11 in here. We're going to write age, let's say we're writing 11 in here, and we're going to write age in here. And then we have a couple of characters that are outside of this box. Now in C, this will work perfectly fine, and we can just print string first, and it will print the whole string. But we've clearly violated the type system of C, or we're clearly like accessing data outside of the box. And this is pretty common in C and other low-level software, where C is intended as just a thin layer over assembly language where we follow or trust the programmer to know how the memory layout should look like, which also means that the programmer is responsible for handling memory. Back in the days, machines were slow, memory was tight, and the type system was not supposed to constrain programmers. Right? If you tell programmers know what they are doing, everything will be fine. It's a great way to keep them happy, right? But it's also a great way to like figure out tricks or to enable tricks around the type system, which can then in the long run result in challenges. This is clearly successful, but times change. Today, correctness and security are far more important, and C's type system is not helpful. Because type safety and type checking is becoming like an automated bug detection mechanism. Right? If the type checker tells you that, hey, like you only declared this as one single character, but you're writing way beyond the bounds of your object, which would prohibit this kind of violation. So string copy would have to be stopped because you're violating the underlying type. Then you as a programmer, you could actually fix this. You could fix the underlying bug and therefore get rid of potential safety issue in the memory allocation that we've just seen before. But even as a type system, you can have bugs. Right? Type systems do not prohibit all kind of bugs because the languages are still Turing complete. You can still miscompute. But the miscompute is going to happen inside the semantics of the programming language and not outside of those semantics. So if you have memory safety errors, if you violate the type system, you can operate outside of the semantics of the programming language and thereby create what is called a weird machine that can potentially be used to trigger any arbitrary computation. Let's take a short. Let's spend 2 more minutes on the last 2 slides because then we can take the break between topics. So the example that we have here for Java, like we have class foo. This is the same example as we've seen before. The length, the string, and here it's not inlined into the object. In the C example here, we just extended the object and made it larger, assuming that the programmer can adjust the typing information as we go along. In Java, this is just going to be a pointer to the string, right? This is a reference to the string somewhere else. When you create a new foo, we store string dot length and a copy of the string, like a reference to a copy of the string. In C, what the risk is, like for type confusion, here we violated the underlying memory typing information or memory typing rules. Here, an example of an actual true bug. There was a message buffer, right? This is very similar to the example we've just seen before. There's a type message. There's an integer message type which defines what type it is, if it's either a name or a name ID. And then we've got the union. It's either a pointer to the name itself, or it is the name ID. And let's say here we set the default message to hello world. We've got a message buffer buff. We say it's a name type. And we store it. We store the pointer to the default message here. Okay? So this writes into this field. we've got the two boxes, and we've got the type, and the name, and this points to default message, which is hello world, right? Okay, so if you initialize this as a this is the name type, and the name points to default message. Okay, a little bit later in the code, there's a bug that says buff.nameID. It accesses the second field, which is a type violation or type confusion. It assumes it's a ID type, right? And sets the pointer to just another integer. And this integer could be like the value controlled by the attacker, right? Because the attacker may be able to set an ID. And here we just do as in a simple example, we set it as a default message +1. Okay? So this is being treated as an integer. Now, later on, printf message, it would print hello world because we skipped the h and just created an arbitrary pointer somewhere into the middle of this string. Now, buff.name is now hello world, even though it's not directly modified, resulting in the underlying bug. So the the attacker could create an arbitrary pointer somewhere into the address space and then abuse it later in an exploit. There's no type check, right? You can just abuse the C type system, and the programmer is responsible for not making these mistakes. And it's very easy to make these mistakes, especially if you're writing 100 million lines of code. You don't know, you may know 1,000, 2,000 lines of code. You keep the context of a couple of thousand lines of code in your head. Anything beyond that is just too complex for you to keep track of. So don't make these mistakes. I want to quickly add some more detail. There was a lot of confusion regarding C programming. Let me iterate through this again. And I'm aware that not all of you are C programming experts. I maybe should have gone through this in a bit more detail. If we look at struct message buffer, we see an int message type, and then we see a union. The union tells the compiler that anything in here is always using the same memory slots. So we have one 4-byte memory slot, and we're assuming a 32-bit system for the moment. We have one 32-bit slot for message type, and one 32-bit message slot that can be either interpreted as a pointer to a string or as an integer. And now the programmer is responsible for using these two fields in the correct way, both of which point to the same bytes in memory. Now if you look at the bug here, is we are telling we're setting the message type to name type, which means that the programmer is only allowed to access the name field, because the name field and the name ID field both point to the same 4 bytes in memory, right? So we're setting the name field here, and everything is fine. Now the compiler does not know what message type means, or that you as the programmer, you're specifying the type in here. You as the programmer are responsible for it. Now the programmer here made a bug that an attacker could set an arbitrary value, an arbitrary integer value into the name ID, because the attacker was able to set the name ID here, which thereby overrode the pointer that we set before. Right? So these two, name ID and name clash. So this assignment here overwrites, through this type violation or type confusion, the pointer to name. And the attacker nicely chose default message plus 1, so this existing pointer, and just increment it by 1, which then results in hello world instead of hello world. I hope this clarifies that aspect a bit. If not, do ask more questions. Cool. So we talked about type safety. I already mentioned memory safety a couple of times. We're going to look into memory safety in a bit more detail. So memory safety is an essential programming language property, which means that code can only access data within live regions of memory whose pointers are properly defined. So here we've got an array with known upper and lower bounds, and I must be inside these bounds. So I must point somewhere into this array and not outside it. This is the definition of memory safety. Now, the runtime system should detect and prohibit accessing data outside of these bounds and terminate the program if such an access happens. If it does not, this is a so-called memory safety violation. Memory safety ensures that only valid objects are accessed inside the bounds. We have spatial and temporal memory safety. Spatial means that everything is only accessed in bounds. So after pointer arithmetic, we may have to check. Temporal safety means that the underlying object is still live and hasn't been freed or reclaimed or something like that. So the underlying object has not been freed. So a memory corruption is the definition of an unintended modification of a memory location due to missing or a faulty safety check. And in this example here, we don't have a bound check for user 1, but the attacker, this is in C, could provide an integer user 1, and the array is provided by the system. Right? So if the attacker provides a value to user, it could be beyond the length of the array. Right? So if you're looking at this, maybe let me visualize this. So we've got array here. This is, and if we supply user 1 as 0, we're accessing this element here, right? Like if user 1 is 0, we're accessing this element. If user 1 is 5, we access this element here. If user 1 is minus 20, we access this byte here, which is outside of the array. If it is plus 10, we access this byte over here, which means we're accessing data outside of the array, which results in a memory corruption. So spatial memory safety errors, like in this example here, we have a buffer of 12 bytes. We have a pointer to this buffer. We write 10 to it, increment it, then we write 42 to it, which means that we are writing 42 outside of this buffer, somewhere into no man's land, where this results in a memory corruption. Right? And there's nothing in C that prohibits you from incrementing a pointer past the end of the buffer. Right? So, like this one, char pointer equals buff 11, points into the last element of the array. If we increment the pointer, we are now one element past the end of the buffer. If we write to it, this results in a memory corruption. Just having a pointer outside of bounds is not a memory safety violation. A memory safety violation only happens when you read from it or when you write to it. And then bad things happen. Temporal memory safety violations are, we have this buffer. At one point in time it is being freed, but later still accessed, right? Having a pointer to an object has been freed is perfectly fine, only if you access it by reading from it or by writing to it is when a memory safety violation happens. How can you prohibit memory safety issues, especially in C and C++, or in any other language? You can do bounds checking, right? So you can check if every access is inside the bounds. You can do lifetime tracking, where you track the lifetime of individual objects, and you can do different kind of automated storage reclamation, such as garbage collection, reference counting, or smart pointers, right? So bounds checking is for to protect against spatial memory safety violations. Lifetime tracking and garbage collection would prohibit against temporal memory safety violations. So if you're looking at array access, like a simple approach would be to store the length of an array along with the array. Now, array access, like this would be a pseudo code for an operation that does a check, where we have a array, size, and index, and we would always check if index is larger than size, and then return either 0 or an error or something else. Otherwise, we return the value at the index. Right, so this is a pseudocode operation for checking this. Now, in C, like one of the very early decisions, there was a discussion when the language was created, if arrays should have a field that contains the length. If structs should have a field that contains the length. It was decided against adding this because this would waste memory and programmers would know what the size of the memory actually is. Right, so this was a very early performance optimization in the 70s that brought us all the security bugs that we use today. Right, so it's a very long lifetime of these issues. It can be traced back to the decision of not having an array, like an array length index, array length field in arrays. In Java, the underlying runtime system, or the underlying runtime environment, the virtual machine, when it allocates an object, an array object, it stores the length of the array in the very first slot. So the array is the length of all the elements plus the integer to store the actual length. And that way you can actually implement bounds checking as you're working with it. And the Java compiler, the just-in-time compiler, will add these bound checks as it's compiling the code to make sure that out of bounds cannot happen. Rust, similarly, automatically insert bound checks for slices. If you define a slice of an array, it implicitly adds a bound check and aborts when the index is out of bound. So if you look at the code, right, if you compile Rust code and disassemble it, or look at the assembly code, we see that if there's an out of bound, like it checks the length of the index is being accessed against the actual length. If it is above or equal, it jumps to out of bound. Out of bound just errors out and terminates the program. Right, so these are extra instructions that are implicitly introduced by the compiler to prohibit an out of bound access and terminate the program if something like this happens at runtime. Right, so this is an automatic check that is inserted by the compiler to enforce spatial memory guarantees. Bounds checking is not free. Softbound is an implementation of spatial memory safety checking for C, and it comes at around 70% overhead. And particular issues are that C has a lot of arbitrary pointer arithmetic that needs to be checked. Different kind of like a pointer and an array is pretty much the same. Like a reference to an array is the same as a pointer. And the programmer actually sees and can observe the memory layout, which makes modifying pointers and tracking bounds information extremely expensive. So if you look at softbound, a large part of the overhead does not come from the actual bounds checks that you have to do, which Rust also has to do, but from actually tracking the bounce information across different assignments. So a large chunk of this overhead is due to the tracking of the bounce information across all the different assignments. For Java, because the code is being assumed to be memory safe, the overhead is only 3 to 10%, a couple of percent. It's roughly the same for Rust, depending on how you write it. You can be, like, we are paying about 3% of performance overhead for protection against spatial memory safety violations. That's a very, very low overhead to pay. And I think 3% is a number that people would be very much willing to pay. 70% goes beyond, right? And this is the only difference here is the programming language. In Rust, the programming language is built so that you can actually add bounce checking. In C, with the conflation of pointers and arrays, the program revisable memory layout and whatnot, it's next to impossible to implement this efficiently. So you have to, in C, you have to implement some disjoint metadata information to keep track of bounce information because you cannot do it inline, which results in this massive amount of overhead if you're tracking it. So far so good. We're doing this for bounce checking, but we also need to protect against temporal memory safety violations. And this is where garbage collection comes in. And the garbage collector, the idea of garbage collection is that, like, we don't worry about freeing objects, we just let them around. And every now and then we scan all of memory and figure out which parts of memory are still being used and which memories can be reclaimed. This prohibits or circumvents errors such as double free, use after free, or not freeing. Like, if you are responsible for memory management, as you are in C and C++, you may free the same object twice, which is called a double free, which can corrupt data structure. Something could be used after free, right? So an area of memory could be used after the underlying object has been freed, which is difficult or a security violation because the same memory could already be used for another object, for another type, or not freeing, resulting in a memory leak. There's reference counting, garbage collection, and whatnot. Now, if you look at temporal memory safety and security, if you do double free, that's an issue of integrity. As the libc memory allocator stores a lot of metadata next to the allocated objects, freeing memory chunks twice will overwrite the secret information. So just as a note, right, what I mean by that, if you're allocating an array like this, like you do malloc 16, the memory allocator would write some additional metadata on the side right before to keep track of it. When you free it, the memory allocator looks at this metadata and uses this as information to free the object and will store some other pointer in here when it adds it back to the list. If you free it twice, this data has obviously been corrupted and you're using the wrong data on it. So this means that there's potential issues for reuse. A solution to this is reference counting, where every block of memory contains a number, has an integer field with a number of pointers to it. Whenever you allocate the block, it is initialized as 1. When you copy a pointer, it is incremented. When you drop a pointer, it is decremented. Very simple, but very fidgety to get it right, because you have cycles or whatnot and other different kind of issues that run into. The underlying object is freed immediately when the last pointer drops to 0. There's no pauses, right? This just runs very, very efficiently. But the increment-decrement overhead can be significant and complex. Especially when there's cycles in a graph. Like, for example, in a doubly linked list, you will always have a count that is larger than 0. So this would never be freed, and you have to explicitly set it. For example, Python or PHP implemented these kind of reference counting algorithms. That's an example. We do array X is an array consisting of 1, 2, an object. So we have in a global scope, when we start with the global scope, we have the array X, which points to a list that has 3 entries, 1, 2, and a pointer to an object instance. We create a second reference to Y. We create last, which points to the last object. We pop it, which creates removes it from the list, and when we delete the last, it removes it. Right? So that way, reference counting can count the number of references pointing to it. There's currently 2 pointing to this list, that's why it's not going to be freed. But on the other hand, after deleting last, the last reference is being removed, and we can reclaim the underlying memory. Garbage collection is a slightly different approach. The idea is, we'll delay this as long as possible. Whenever the program runs out of memory, we stop the world and we run the garbage collector to find any unreachable objects. So this pauses the program execution for a couple of milliseconds up to seconds, depending on how much memory needs to be reclaimed, and there's an interesting trade-off between the different options. Uncollected garbage before you run the collector increases the memory requirements, as there's a delay between when memory is no longer reachable and when it is being reclaimed, and during that time this memory is not available for other processes. It may be cheaper than reference counting because you don't have to keep track of the actual pointers, but you're only doing actual work when you are reclaiming the memory, when you're scanning the whole heap. It easily collects unreachable cyclic data structures, and it's being used in JavaScript, Ruby, Lua, Java, whatnot, and everything else. A common example of a garbage collector is mark and sweep. I think that's one of the simplest ones. So at any point in time, you start with a root set. A root set could be, for example, all the global variables, because they're always going to be there, because they're global, and any pointers you have on the stack. So mark and sweep means you start from the root set. So you mark all of these pointers, which would be marking objects 1 and 6. So you add objects 1 and 6 to your work set, and then you go through all the reference objects there, which would be objects 2, 3, and 4. So you add them to the working set. You go to object 2, no additional ones, object 3, no additional ones, object 4. You have a backward pointer, you're good. We've now marked all the live objects. We've marked all the live objects, which then means that the garbage collector can sweep and free all the unmarked objects. Right? And this can be implemented rather efficiently, even concurrently. There's compacting versions to it. There's different optimizations to reduce the overhead, and it works reasonably well. Right? So you first mark all the objects starting from the root set, iterating through each of them in a work list algorithm. As soon as your work list is empty, you reclaim all the remaining objects that are there. So far, so good. What's the overhead? Garbage collection overhead is difficult to measure. You don't really know. It can improve performance, because if your program finishes before you have to run the garbage collector, when you terminate a process, the memory is freed automatically. Then you don't need to spend additional overhead. But if you have to run it frequently on a very constrained heap, like you only have a very small set of memory, it may cause significant performance overhead. Also, it's hard to figure out what the baseline is. What do you compare against? How would you do this against another implementation? It has a negative reputation, but it really depends on how the program is actually being written. If you allocate billions of objects and then just drop them right afterwards, it's yeah, it's not ideal. So this depends more on you as a programmer than as a technique by itself. An alternative to garbage collectors, there are garbage collectors for C and C++, but they are usually extremely slow. Now, I'm very much aware that I'm repeating this reputation, but in Java, a garbage collector can be efficient because the language supports garbage collection. The language is designed to enable garbage collection. C and C++ are not designed for garbage collection, which means that you have to go through a lot of extra steps of doing reasonable garbage collection. So in C, C++, as an alternative to garbage collection, the issue was that they introduced smart pointers for automatic memory management. It's not mandatory to use them, but if you're using a modern programming style in C++, you will actually use a form of smart pointer. Smart pointers free their reference content when it goes out of scope. And there's different types. There's unique pointers, so this means this is a unique reference to an object. If you have a unique pointer, you cannot copy it. If there's shared pointers, it's a reference counted pointers, or you have an implicit field for reference counting that is added in this type. You can use weak pointers together with shared pointers to break reference cycles. Now, interestingly, as a programmer, you will have to get used to using these different kind of smart pointers, and there's still like different kind of bugs you can have in your code by using weak pointers if you're not using them correctly. Now, as an example, here we've got our smart pointer class. There's an actual pointer in this class in there, and then we have an explicit smart pointer initialization where we initialize the pointer being given. So it's like a wrapper around an existing pointer. When the destructor for the smart pointer is being called, we delete the original pointer, so we free the target area when it goes out of scope. And the dereference operator is being overloaded to just return the internal boxed pointer. When we use it here smart pointer is new int. We can set a value to pointer. We can print it. And when it goes out of scope, right, when we close this scope, this local stack variable, the smart pointer will be deallocated, which calls to the structure, which then frees the underlying memory object. Right, so it's a nice way to bring like automated garbage collection or like automated memory management to C++, where you don't have to worry about freeing objects. What's the alternative to C++? It's Rust. And Rust is a new systems programming language that aims at replacing C and C++. It's a modern language that leverages a lot of the concepts that have been developed in the last 20, 25 years in program language design, making it a statically checkable programming language with a very strong and strict type system, where if the type checker validates your program, you're certain that there's no memory safety violations and no type safety violations. So there's no way to escape the type system, which is the biggest advantage of Rust. It gives you a lot of the safety guarantees, but also the biggest disadvantage of Rust, because fighting the borrow checker is extremely painful for anybody who ever wrote Rust code. So Rust has a notion of explicit ownership on who owns or which part of the code own certain data to like limit or remove the need for garbage collection. Enables low-level programming. It's very efficient, no garbage collection, and the abstractions boil down to very simple mechanisms. It's becoming rather popular, so it's being used in Android, as I mentioned at the beginning of the class, but also in the Linux kernel. There's larger chunks being written in Rust, and especially for new components, it makes a lot of sense to use to write these components in Rust. Rust ownership works as follow. Like variables own the value they are bound to, as in they contain. So variables own the different data they point to, and when a variable goes out of scope, the value is deallocated. Similar to the smart pointer that we looked at for C++ just a minute ago. Key restrictions that exactly one variable can be bound to a value, like a unique pointer in C++. So unique pointers and Rust references are pretty similar. It's a step forward from C++ smart pointers as it is mandatory, right? You're forced to have this. And the compiler strictly enforces the constraint. In C++, you can always just cast this into a void pointer and then do anything with it that you want. Here, for example, we declare a vector 1, 2, 3. We have v2 equals v. We do an assignment, and then we do a print. Whereas hey, this is an error because you're actually using data that has been moved. Because there can only be one owner. After this assignment here, v2 is the owner of this vector, and v is no longer the owner. V no longer has access. So if you access v, this is an error that the type checker will tell you that it doesn't work. Rust enables a concept called borrowing, which is a way that allows the system to give access to a variable somewhere during the execution and then return it. For example, for a function call. So borrowing handles this common situation by sharing the ownership between two variables, as long as the borrower's lifetime is no longer than the owner's lifetime. Like if you borrow a reference, you have to give it back to the owners, which means that the owner must outlive the borrower, and either one writer or multiple readers. So here in this example, we've got v1 is a vector, v2 is another vector, answer equals foo with references to v1 and v2, which means we can use v1 and v2 later on here, because we say that, hey, we're just borrowing these two vectors. The reference is immutable. If foo would change it, we would need a mutable reference and thereby exclusive access to it. Read-write restrictions. We cannot have mutable and immutable borrows to a value at the same time. Here in this example, we let mutable x equals 5 and y is the reference. Here, if we have a debug print of this variable, it would just throw an error. The compiler would tell us we cannot borrow x as immutable because it is also borrowed as mutable, and the two borrows conflict with each other, which means there's an exclusive relationship there. Now, Rust ownership is a pain. The handling ownership, handling references is extremely challenging in Rust, and it's a big theme in how to fight the borrow checker. And implemented as a linked list is a meme in the Rust community itself, because a linked list is one of the simplest data structures you can implement in any programming language. And in Rust, it's surprisingly complicated because of the references and how individual items own each other. There's an 8-chapter book on different ways to implement linked lists, which is fairly significant, especially as you can implement a linked list in about 10 lines of code. A single linked list is already quite verbose, and you need to use two different features called option and box. Doubly linked list is even more challenging due to cyclic references between the previous node and the next node. Okay, folks, let's continue. Thanks for all the questions regarding Rust. We're now going to go through a couple more details. I don't expect you to program in Rust at the end of the course. The goal is for you to be a bit more familiar about the different programming languages and maybe have a glimpse of the different targets. Maybe get a bit more familiar with the one additional language that you may get across sometime later in your careers. We talked about Rust, right? So implementing a linked list works as follows. One of the many different implementations that can be discussed at length. Is the following one: struct node data is of type i32, as in a 32-bit integer, and then next it's an option that's a boxed node, right? So we need to wrap the next field is a node that is a box and an option. Box is required as otherwise the node references itself, and the Rust type checker will figure out or will decide that this type needs infinite memory because it keeps referencing itself, and therefore error out. Option is needed because of the tail of the linked list does not have a next node, and null pointers do not exist in Rust. So therefore it's an option, which means it's an optional data field. So in the last node, it's not going to be used, but in all the other nodes, the next points to another node. And which means that for ownership, the current node owns the next node. Right? So the ownership is handled that the current node owns the next node, and this is how it's implemented. Now, which obviously makes the insert delete operations a bit challenging, especially if you want to remove inside the linked list, because you have to adjust the ownership correspondingly across the two sides. For a doubly linked list, it gets a bit more complicated. You actually need reference counting, right? Because the previous and the next cannot own each other, which would mean that you have multiple owners, right? You have the node before you, and you're being owned by the node before you and the node afterward, which conflicts with Rust's one single owner assumption. Right, so instead we'll have to use reference counting, which is called RC, to figure out the different targets. We again use option because the first and last don't have previous or later nodes. And ref cell is needed for interior mutability for inserting or deleting nodes. You still need to implement a custom destructor to avoid memory leaks when you're freeing information, so that the reference counting cells are actually set to 0 in the correct way, which is quite complicated for a very simple linked list. And it still has not so great performance due to multiple layers of wrapping. So, which means that in Rust you don't necessarily would want to implement a linked list like that, right? This is not a comfortable way to implement it. You don't want to think about these abstractions. That's why Rust has an escape hatch, right, and allows unsafe code. And unsafe code pretty much means, dear borrow checker, dear type checker, trust me, I know what I am doing, right? And don't look at this, right? This is the ugly stuff that we are doing to get to fix things up. So this is a way how you can implement code that would otherwise not pass the borrow checker. So you put unsafe code in a module and wrap it in a safe instance to use it in the rest of the program. And then in the few lines of code that you modify, you can have unsafe blocks that allow you to do pretty much anything. And it just tells the type checker and the borrow checker, please don't look at these lines of code, they're good, trust me. Now, is this safer than C or C++?
Definitely the same.
It's the same. It is the same for these few lines of code. In C and C++ code, you have to, everything is unsafe. In Rust, hopefully in 100,000 lines of code, you've got 50 lines that are unsafe. Right? So the idea is that, it's much, for a linked list, it's much simpler to implement a linked list in unsafe code. Because the ownership, the idea of ownership just goes into, conflicts with the implementation. So linked lists, trees, and whatnot are all implemented in unsafe Rust. But like a 20-line, 40-line implementation of unsafe Rust, you can actually formally verify. Right? So you can formally verify these data structures and get safety that way. Like as in you're using the escape hatch of unsafe Rust, but then actually can formally verify to make sure that this is still safe. So unsafe code, for example, growing a vector here, like a vector grow, we check if the capacity is 0. If it is 0, we go from 0 to 1. This is when we allocate the vector. Otherwise, we double the capacity. Right? So this is an exponentially increasing vector, which is usually the way how vectors are implemented. New layout, right? You grab the new the array layout. If cap was 0 before, you just allocate the new layout. Otherwise, you do a realloc. And alloc and realloc needs to be wrapped in unsafe to update all the different references in here. And it's a nice escape hatch, how you can interface with the underlying system without being too complicated and dancing around these issues. Now, as we've discussed before, should we rewrite everything in Rust? Well, in most cases, it's just not possible. Right, the core of the Chrome browser is 33 million lines of code, with about 60 million lines of code in support libraries around it that are all written in C and C++. The Linux kernel is another 30 million lines of code. It's just too much to rewrite, and by rewriting them, we would introduce a lot of bugs that may not be memory safety bugs, but all the other types of logic bugs, as in like how to handle certificates, how to decode image formats, how to safely store and update information, how to manage different data types and whatnot. Right? So for old code, employ fuzzing as part of continuous integration, mitigations and hardening as in different kind of defense and depth strategies. And our hope is that through continuously testing, we get rid of all the bugs that are exposed. New code. If you're writing a new project, prefer a safer language like Rust if it needs to be fast, or Go or Java or Scala if you don't mind performance that much, and you can go for comfort of programming. If you only need to write it once and execute it once, use Python. Right? But if you need to use it multiple times, pick a language that suits the implementation. So clean slate is not needed, right? Simply writing new code in Rust is sufficient. And we see this as the number of memory safety vulnerabilities being reported actually go down. Now, this is what's claimed in a Google blog post from like 2 weeks ago, I think, or 3 weeks ago. Now, I am somewhat dubious that the amount of memory safety errors actually goes down. There's still code being rewritten or changed in C and C++, which exposes new vulnerabilities. So what we've seen here is, what they didn't show is like 5 years before, it was like this, right? And then it went up and down, which correlates, this up and down, correlates with massive deployment of fuzzing over the last, like fuzzing started 2016, and we went from about this to up here, and now we're going down. I think we've just hit the peak of fuzzing. What this figure indicates is that it is trending downward. My projection is that we're going to end up like this. It's going to be flat. Because we now have gotten accustomed to fuzzing, and all the easy bugs are found, but there's a continuous source of new bugs. So we'll continue on that, very likely. But we'll see. It's very hard to make predictions, especially about the future. So we'll see how this turns out. Let's move on. We've now talked about memory safety. We've talked about type safety. The next big ticket item is thread safety, where code runs in parallel and multiple threads have access to the same data. Since about 20 years, our processors are no longer getting faster. In fact, over the last 20 years, our processors got slower. Like if you look at single core performance, this peaked in about 2004. When we had like 4 gigahertz beasts that were extremely like power hungry, burning through a couple of 100 watts, but providing pretty good performance. Now, even like my smartphone has 16 cores, but each of those cores is much less powerful than a machine from 20 years ago. Right, so it's an interesting trade-off where instead of going for one super powerful core, we're going for many cores that are not as powerful because they're easier to manage. Now, the difficulty is for the programmer actually having to figure out how to program these systems. And this is where all the thread safety issues come in. It's much easier to write single-threaded code than writing multi-threaded code. As everybody knows, whoever wrote the multi-threaded program. So thread-safe code only manipulates shared data structures in a manner that ensures that all threads behave properly and fulfill their design specifications with unintended interactions. So potential concurrency bugs could be race conditions where 2 threads are accessing the same data without coordination. Like 2 or more threads attempt to access and modify the data at the same time without locking the data before or synchronizing on who's allowed to access. Could also be a deadlock, right? Deadlocks are 2 or more threads are blocked forever, each of them waiting for the other thread to unlock. Let's say you have 2 pieces of data for a simple transaction. The account you send, you take money from, and the account you send money to. Right, so you want to decrement one and increment the other. And if there's 2 transactions in parallel, one decrementing this one and one decrementing this one, like if they're running at the same time, the two threads could take both locks and then waiting for the other lock until the rest of time. This is a typical example. So deadlocks are bad and can have can stop your program from making progress. Race conditions are even worse because you're actually miscomputing and potentially missing updates, potentially missing writes, potentially missing data values, or destroying values in process. A recent, semi-recent interesting bug was dirty cow. Cow or copy on write is a technique used in operating system kernels to save memory. So when you create a new process, you fork, you take one process, you turn it into 2, and the 2 processes are copies from each other, where the only difference is the return value of the fork system call, if you think back about your operating system class. Right? So the only difference is the return value of the fork system call. How would you implement this at the operating system? Either you could copy the whole address space, which would be quite wasteful, or you mark all the pages of this process as read-only until you touch it. So as long as neither process writes to it, you can just share the memory pages. As soon as one process writes it, you need to copy it over and actually allocate a memory page. So the first time a process writes to it, it is being the underlying page is allocated. And in the Linux kernel, there was an issue in this copy on write implementation that allowed an attacker, like if the memory pages were related to file descriptors, to turn read-only file descriptors into read-only pages into writable pages, which is quite bad if you have a writable page that then contains code that is used in another location, and you can modify the code of another process. Right? This was an very interesting bug in the Linux kernel that allowed privilege escalation to root. So these bugs are quite severe and also very, very hard to find because they're hidden somewhere deep in the operating system kernel, in this example, somewhere deep in your program. And in most cases, this is not, like you will not find it, right? Because the regular execution is just, the timing just doesn't align to trigger it. That's an issue with all of these concurrency bugs. The timing has to be exactly right to trigger the bug. So thread safety in programming languages, modern languages include type-safe synchronization primitives, such as either locks, semaphores, atomic variables, and whatnot, and thread-safe language constructs. In Java, we have the synchronize keyword, which means that only one thread at a time can execute the method on an object. If there's multiple threads trying to execute the same method on the on this object, they would have to wait. Go, we have Go routines and channel, and in Rust we have ownership. And these modern language features make it easier to program a thread-safe program. It's still the programmer's responsibility for correctness. So for Java, we can use the synchronized keyword, and the method inc would increment this private variable here, which means that if you have a counter object and multiple threads trying to increment, they would have to like wait until they get to lock and can then update the target value going forward. In Go, the concept is different, and I think that's the most interesting addition of Go as a programming language. The idea is don't communicate by sharing memory, share memory by communicating. And Go has this idea of channels. Right? Go routines, these are threads created by the Go Go runtime, very cheap, very fast, using a special form of scheduling. And then through these communication channels, you can send data. Data is copied from one end to another. Here we've got messages. We make a channel with a string where we send strings through. And here in the Go functions is a concurrent thread that is being spawned, and we write the ping into the messages channel, and then in the main thread we read out the first message and print it. And the synchronization is done by the underlying operating system. It's a very beautiful way of abstracting the difficulties of writing concurrent programs. Thread safety in Rust. In Rust, we use the same mechanism that guarantees temporal memory safety to ensure thread safety, namely ownership. So either a single owner that allows to write, or multiple that are allowed to read, which prohibits different kind of data races. If you mistype, or you would borrow across multiple writers, the Rust compiler will complain and tell you that there's an issue. You can actually list this up, and for example, here in this thread, you could move the ownership of this vector into the spawned thread, and then the parent will be prohibited from accessing the underlying data until the assignment returns, for example. Right, and this way, if you want to keep access to the data, it can be wrapped into a mutex, which is a new type that allows us to have mutual exclusive access to it. Wrap it, and inside the new thread, you can access it by unwrapping it and locking it, or outside we can do the same, which then again enforces a communication primitive that the runtime system can leverage to synchronize the different parts. So, short summary for thread safety: you need to use the underlying primitives. Now, in C and C++, you are solely responsible as the programmer, same as for memory safety, to implement these abstractions correctly. In modern languages like Go or Rust, or Java for that matter, it comes with primitives. In Java, not that much, because in Java you could forget the synchronized keyword. If you don't do synchronized, you have all the thread safety issues. Java itself is memory safe, but not thread safe. It does have nice keywords, though, that you can use if you want to, but you still have to use it. In Rust and Go, the language itself enforces the correct use of these communication primitives. And it's like a built-in functionality of it. Sandboxing and compartmentalization, last topic for today. Recall the principle of least privilege. Principle of least privilege ensures that a component has the least privileges it needs to function, which means that we have removed all the extra capabilities that we don't need. No extra functionality is present. Any additional functionality that is removed would impact some functionality. Any functionality that is added would not increase any other functionality. And it's an interesting core principle of security. We should always strive for least privileges. Sandboxing allows us to implement least privilege by running programs which can often be untrusted code in an isolated, restricted environment. So, for example, Docker containers are a form of sandboxing where you can specify which system calls are being allowed. Or seccomp is another form of sandboxing where you can specify this process is only allowed to execute these 5 system calls. It's often an implementation feature of programming languages instead of a design feature, but yeah, this depends a bit on the context or whatnot. The 2 main examples that we are using today, as I said, are seccomp or C groups, examples of which are SC Linux or Docker. They've gotten pretty good use in the last couple of years. So an example of where we use sandboxing is JavaScript or WebAssembly inside the browser, interpreters embedded inside word processors, such as for GhostScript, VBA, or whatnot, and without explicit permission from the user, a web page or document shouldn't kind of leak secrets or get access to your local hard disk. Sandboxing promises security, but relies on the underlying implementation of the sandbox. So a sandbox can be implemented by the kernel, for example, such as the Linux kernel doing this Docker or seccomp. It can also be implemented in software, whereas you get additional difficulties. So for example, for WebAssembly, the sandbox is implemented through a checker where the compiled code is being checked to adhere to certain criteria. If all of these checks turn out to be successful, then we know that the code will never branch outside any of a particular. There's no undirected, indirect control flow to uncontrolled targets, for example. Sandboxing is hard to get right. So both for Docker, but also for seccomp, but also for NACL native client, the precursor to WebAssembly, and for WebAssembly itself, there were many escapes or sandbox escapes, but we're getting much better. If you're looking at WebAssembly, Docker, and whatnot, the number of vulnerabilities we find these days is much lower than just a couple of years ago. Some of you may remember Flash or Flash games. Flash used to be a thing in the web. Late 90s, early 2000s. The only interactive content on the web was through Flash, and Flash lived until around 2015, 16, 17, but was prone to vulnerabilities. So the implementation of the Flash runtime, which ran as a plugin inside your browser, was pretty much horrible. And there was like a constant barrage of security vulnerabilities. It was the most buggy component in the browser that was being used. And there used to be security nightmares. Luckily, they died, and we got rid of the Flash plugins. Partly because JavaScript has just gotten powerful enough. JavaScript has become fast enough so you can write arbitrary programs in it. The very reasonable performance. But yeah, sandboxing is hard to get right because you need to make sure there's no way to escape the sandbox. Compartmentalization requires sandboxing or leverages sandboxing to potentially enforce these privileges. And the idea of compartmentalization is to break a large complex system into a lot of small individual components. And then you limit the individual boxes from accessing each other directly and enforce that they have to go through a very specific API. The difference here is if a breach happens, you no longer have access to the full set of data, but only to the first compartment. And you need to use the API between the two compartments to actually follow up. Right? So the idea is that the attacker gets access only to the data of the compartment. If they want to escalate their privileges, they have to break into each other apartments. So instead of having one bug to access all of it, they need additional bugs. And if the secret is in this compartment here, they need 1, 2, 3 other additional bugs to go through. Right? And this makes this much more complicated. Compartmentalization is used as, for example, in Chromium for sandbox render engines. This is what I mentioned before. Rendering HTML, CSS, and running JavaScript is horribly hard. Like, it's extremely difficult to get this right. It's the most complex code in the browser, also the most buggy code in the browser. This is why the render engine, which renders HTML and kind of turns it into a tree of an information tree, a DOM tree. This is being done in a separate compartmentalized process. Now, this starts as a new process. You establish an IPC channel to communicate with this process, and then the process drops all writes, like writes to all the system calls except for returns and exits, and only communicates through this IPC channel that was already open. So it can only use the system calls read, write, signal, return, and exit. So this is a very nice way to limit the risk, and therefore all the code that is being used, all the possible buggy code is being contained in this tab. Now, is this the best possible way to compartmentalize, or what's missing here? Especially if you think about the slide we just had before. Is this enforcing least privileges? It's not enforcing least privileges, right? It's still like the render engine has like 10 million lines of code in it. Now, why is this the case? The way how compartmentalization is implemented is it runs as at an individual process. So each time we are sending data into this process, or when we are reading from this process, comes at a performance cost. So each time we interact with the compartment, we're paying performance overhead. Ideally, we would break this into much smaller components, but we can't at the moment due to the performance cost of context switching between processes. So again, here we have the trade-off between security and performance. Like, we are limited by the amount of performance overhead we can take. It's still a great step forward, but it's not perfect. There's also compartmentalization being pushed into programming languages. So the idea here is that we potentially want to compartmentalize at the library level, at the software level, or even making it an explicit feature in the programming language. So there's an enclosure paper, language-based restriction of untrusted libraries, where you can actually compartmentalize libraries on their own based on whatever data they use, giving you the power of using compartmentalization as a language feature, similar to memory allocation or memory management or thread concurrency management, right? Compartmentalization must become a language feature to actually enable this throughout all the different targets. In the homework, you will play with different kind of mechanism translating step by step with guidance C to Rust code to get a little bit of a feeling of what the how bugs in C code look and how safer versions could look like. And you'll play through a different through a set of examples to get a bit more of a feeling of how this actually works. The goal is not that you become expert C programmers or expert Rust programmers, but that you get somewhat of an understanding of how these bug patterns and so on look like. So let me summarize. Memory safety issues remain dominant. They're still like a key attack vector used on today's systems. Modern programming languages achieve memory safety through bounce checking, lifetime tracking, automatic storage reclamation, by making this a feature of the programming language itself in the runtime system, by integrating the security concepts into the programming language. Programming languages type systems can be static, dynamic, inferred, declared, strict, relaxed. It is key that type systems should be strict for security if they are too relaxed. And they can be circumvented, such as in C, as we've seen with the example. A developer can get around the safety constraints of the type system. Same for concurrency. Modern languages provide synchronization primitives. For C, C++, and Java, this is implicit, right? As a programmer, you can use the synchronization primitives, but you're not forced to. And we also see that all these older languages, they were designed before 2004, before we had multiple cores. Right? Now we have multiple cores, and modern programming languages have synchronization primitives built in and enforce that. And sandboxing and compartmentalization to then enforce least privileges on top of it. That's all for today. If you have questions, I'm going to stick around for a couple of minutes. If not, I will see you in 2 weeks. Not next week, but 2 weeks? 3 weeks? 3 weeks. Oh, yeah, there's a break also. Cool. Thank you.